X-ray photoelectron spectroscopy, XPS. David Echevarria Torres. University of Texas at El Paso. College of Science. Chemistry Department. Outline XPS background. XPS instrument. How does XPS technology work? Auger electron. Cylindrical mirror analyzer, CMA. Equation. K versus P. Spectrum background. Identification of XPS peaks. X-rays versus E-beam. XPS technology. XPS background. XPS technique is based on Einstein's idea about the photoelectric effect, developed around 1905. The concept of photons was used to describe the ejection of electrons from a surface when photons were impinged upon it. During the mid-1960s, Dr. Siegbahn and his research group developed the XPS technique. In 1981, Dr. Siegbahn was awarded the Nobel Prize in Physics for the development of the XPS technique. X-rays irradiate the sample surface, hitting the core electrons, E, of the atoms. The X-rays penetrate the sample to a depth on the order of a micrometer. Useful E signal is obtained only from a depth of around 10 to 100 A on the surface. The X-ray source produces photons with certain energies. MgK photon with an energy of 1253.6 electron volts. ALK photon with an energy of 1486.6 electron volts. Normally, the sample will be radiated with photons of a single energy, MgK or ALK. This is known as a monoenergetic X-ray beam. Why the core electrons? An electron near the Fermi level is far from the nucleus, moving in different directions all over the place, and will not carry information about any single atom. Fermi level is the highest energy level occupied by an electron in a neutral solid at absolute zero temperature. Electron binding energy, B, is calculated with respect to the Fermi level. The core ES are local close to the nucleus and have binding energies characteristic of their particular element. The core ES have a higher probability of matching the energies of ALK and MgK. Core E. Valency. Atom, binding energy, B. The binding energy, B, is characteristic of the core electrons for each element. The B is determined by the attraction of the electrons to the nucleus. If an electron with energy X is pulled away from the nucleus, the attraction between the electron and the nucleus decreases and the B decreases. Eventually, there will be a point when the electron will be free of the nucleus. This is the point with zero energy of attraction between the electron and the nucleus. At this point the electron is free from the atom. X P plus Be. These electrons are attracted to the proton with certain binding energy X. Energy levels: vacuum level, Fermi level, lowest state of energy B. O, which is the work function. At absolute 0 Kelvin the electrons fill from the lowest energy states up. When the electrons occupy up to this level the neutral solid is in its ground state. XPS instrument. XPS is also known as ESCA, electron spectroscopy for chemical analysis. The technique is widely used because it is very simple to use and the data is easily analyzed. XPS works by irradiating atoms of a surface of any solid material with X-ray photons, causing the ejection of electrons. University of Texas at El Paso, Physics Department. Front view of the Phi 560 XPS/ICE/SEMS UHV system. University of Texas at El Paso, Physics Department. XPS instrument. The XPS is controlled by using a computer system. The computer system will control the X-ray type and prepare the instrument for analysis. University of Texas at El Paso, Physics Department. Front view of the Ray+Photoelectron+Spectroscopy+XPS/ICE/SIMS UHV system and the computer system that controls the XPS instrument. The instrument uses different pump systems to reach the goal of an ultra-high vacuum UHV environment. The ultra-high vacuum environment will prevent contamination of the surface and aid an accurate analysis of the sample. University of Texas at El Paso, Physics Department. Side view of the Ray+560 XPS/ICE/SIMS UHV system, XPS instrument X-ray source ion source SIMS analyzer. Sample introduction. Chamber. Sample introduction chamber. The sample will be introduced through a chamber that is in contact with the outside environment. It will be closed and pumped to low vacuum. After the first chamber is at low vacuum, the sample will be introduced into the second chamber in which a UHV environment exists. First chamber. Second chamber UHV. Diagram of the side view of XPS system. X-ray source. Ion source. Axial electron gun. Detector. CMA. Sample. SIMS analyzer. Sample introduction chamber. Sample holder. Ion pump. Roughing pump. Slits. How does XPS technology work? A non-energetic X-ray beam emits photoelectrons from the surface of the sample. The X-rays either of two energies. Alpha, 1486.6 electron volts. Mg-Ka, 1253.6 electron volts. The X-ray photons the penetration about a micrometer of the sample. The XPS spectrum contains information only about the top 10 to 100 day of the sample. Ultra-high vacuum environment to eliminate excessive surface contamination. Cylindrical mirror analyzer, CMA, measures the K of emitted ES. The spectrum plotted by the computer from the analyzer signal. The binding energies can be determined from the peak positions and the elements present in the sample identified. Why does XPS need UHV? Contamination of surface. XPS is a surface-sensitive technique. Contaminates will produce an XPS signal and lead to incorrect analysis of the surface of composition. The pressure of the vacuum system is less than 10 to 9 torr. Removing contamination. To remove the contamination, the sample surface is bombarded with argon ions, R+ equals 3 keV. Heat and oxygen can be used to remove hydrocarbons. The XPS technique could cause damage to the surface, but it is negligible. The atom and the X-ray free electron valence electrons proton. Neutron. Electron. Electron vacancy. Core electrons. The core electrons respond very well to the X-ray energy. X-rays on the surface atoms layers E top layer E lower layer. With collisions. But no collisions. X-rays. Outer surface. Inner surface. X-rays on the surface. The X-rays will penetrate to the core E of the atoms in the sample. Some ES are going to be released without any problem, giving the kinetic energies, K, characteristic of their elements. Other ES will come from inner layers and collide with other ES of upper layers. These E will be lower in lower energy. They will contribute to the noise signal of the spectrum. X-rays and the electrons. Electron without collision. X-ray. Electron with collision. The noise signal comes from the electrons that collide with other electrons of different layers. The collisions cause a decrease in energy of the electron and it no longer will contribute to the characteristic energy of the element. What ES can the cylindrical mirror analyzer detect? The CMA not only can detect electrons from the irradiation of X-rays, It can also detect electrons from irradiation by the E-gun. The E-gun is located inside the CMA while the X-ray source is located on top of the instrument. The only electrons normally used in a spectrum from the radiation by the E-gun are known as Auger ES. Auger electrons are also produced by X-ray irradiation. X-rays and Auger electrons. When the core electron leaves a vacancy, an electron of higher energy will move down to occupy the vacancy while releasing energy by photons. Auger electrons. Each Auger electron carries a characteristic energy that can be measured. 2 ways to produce Auger electrons. The X-ray source can irradiate and remove the E from the core level, causing the E to leave the atom. The higher level E will occupy the vacancy. The energy released is given to a third higher level E. This is the Auger electron that leaves the atom. The axial E-gun can irradiate and remove the core E by collision. Once the core vacancy is created, the Auger electron process occurs the same way. Auger electron 2341 free E released to analyze E vacancy. E of high energy that will occupy the vacancy of the core level. Free E. 3. E released to analyze. 4. 1. E-gun. E vacancy. 1, 2, 3 and 4 are the order of steps in which the ES will move in the atom when hit by the E-gun. Auger electron spectroscopy, AES. E released from the top layer, outer surface, inner surface, electron beam from the E-gun, atom layers, cylindrical mirror analyzer, CMA. The electrons ejected will pass through a device called a CMA. The CMA has 2 concentric metal cylinders at different voltages. One of the metal cylinders will have a positive voltage and the other will have a 0 voltage. This will create an electric field between the 2 cylinders. The voltages on the CMA for XPS and Auger ES are different. Cylindrical mirror analyzer, CMA. When the ES pass through the metal cylinders, they will collide with one of the cylinders or they will just pass through. If the ES velocity is too high, it will collide with the outer cylinder. If is going too slow, then will collide with the inner cylinder. Only the E with the right velocity will go through the cylinders to reach the detector. With a change in cylinder voltage, the acceptable kinetic energy will change, and then you can count how many ES have that K to reach the detector. Cylindrical mirror analyzer, CMA. 0V plus V. X-rays. Source. Sample. Holder. Electron pathway through the CMA. Slit. Detector. Equation. K equals HVBO. K kinetic energy, measure in the XPS spectrometer. HV photon energy from the X-ray source, controlled. O spectrometer work function. It is a few eV. It gets more complicated because the materials in the instrument will affect it. Found by calibration. B is the unknown variable. Equation. K equals HVBO. The equation will calculate the energy needed to get an E out from the surface of the solid. Knowing K, HV and O, the B can be calculated. K versus PK can be plotted depending on B. Each peak represents the amount of ES at a certain energy that is characteristic of some element. Binding energy. Hash of electrons. EV. B increase from right to left. 1000 electron volts. 0 electron volts. E. K increase from left to right. Interpreting XPS spectrum, background. The X-ray will hit the ES in the bulk, inner E layers, of the sample. E will collide with other E from top layers, decreasing its energy to contribute to the noise, at lower kinetic energy than the peak. The background noise increases with B because the sum of all noise is taken from the beginning of the analysis. Binding energy. Hash of electrons. N1, N2, N3, N4. Tot equals N1 plus N2 plus On3 plus On4. N equals noise. XPS spectrum. The XPS peaks are sharp. In a XPS graph it is possible to see Auger electron peaks. The Auger peaks are usually wider peaks in a XPS spectrum. Aluminum foil is used as an example on the next slide. XPS spectrum O1 ZO Auger O because of Mg source CO2's Al. Sample and graphic provided by William Durer, Ph.D. Department of Physics at the University of Texas at El Paso. Auger spectrum characteristic of Auger graphs. The graph goes up as K increases. Sample and graphic provided by William Durer, Ph.D. Department of Physics at the University of Texas at El Paso. Identification of XPS peaks. The plot has characteristic peaks for each element found in the surface of the sample. There are tables with the K and B already assigned to each element. After the spectrum is plotted, you can look for the designated value of the peak energy from the graph and find the element present on the surface. X-rays versus E-beam. X-rays electron beam. Hit all sample area simultaneously, permitting data acquisition that will give an idea of the average composition of the whole surface. Electron beam. It can be focused on a particular area of the sample to determine the composition of selected areas of the sample surface. XPS technology consider as non-destructive because it produces soft X-rays to induce photoelectron emission from the sample surface. Provide information about surface layers or thin film structures. Applications in the industry. Polymer surface. Catalyst. Corrosion. Adhesion. Semiconductors. Dielectric materials. Electronics packaging. Magnetic media. Thin film coatings. References. Dr. William Durer for explanations on XPS technique, Department of Physics at UTEP. www.uxf.com. www.casexps.com. www.nwsl.net. XPS instrument from the Physics Department.